Welcome, group members, to our exploration of 3D printing and Biolink for organ production. Today, we dive into the fascinating world of bioprinting applications. Let's first address the pressing challenge of organ shortages, followed by a clear definition of bioprinting and why this innovative technology holds such significance. Welcome to our scientific teaching video on 3D printing and Biolink for organ production. Let's explore the fascinating world of bioprinting applications together. First, we will delve into the fundamentals of bioprinting and Biolink, understanding how this innovative technology is revolutionizing organ production. Next, we'll discuss the evolution and progress in bioprinting, highlighting the remarkable advancements made in this field. Moving on to applications and benefits, we'll uncover the real-world implications of 3D printing and Biolink in organ generation. But it's not without its challenges and ethical considerations, which we'll address to provide a well-rounded perspective. Finally, we'll gaze into the future directions of bioprinting and summarize the key takeaways from our exploration. Get ready to embark on an educational journey into the future of organ production with 3D printing and Biolink. As a society, we all face the challenge of organ shortages, which leads to long waiting lists and delays in potentially life-saving treatments. Efforts to address this issue include increased organ donation awareness, advancements in organ preservation techniques, and bioengineered organ research. Now, let's delve into how 3D printing is used to create structures that mimic natural biological tissues. This process, known as bioprinting, is essential in fabricating tissue-like structures for medical and regenerative therapies. Bioprinting involves the use of living cells and biomaterials to create complex tissue structures, offering immense potential in organ creation, research, and personalized medicine. As we delve into the world of bioprinting applications, we confront the critical issue of organ shortages. This groundbreaking innovation revolutionizes medical technology by offering the potential for bioengineered organs. Imagine the impact this could have on patient outcomes, reducing waiting times and ultimately providing life-saving treatments. The significance of this technology cannot be overstated when considering its potential for medical breakthroughs. Understanding bioprinting and Biolink is essential in comprehending the role of 3D printing in revolutionizing medical applications. By utilizing Biolink, this technique allows for the fabrication of precise organ structures, contributing to the potential of organ creation. The steps involved in the bioprinting process demonstrate the intricacy and innovation driving this transformative technology. Bioprinting and Biolink play a crucial role in creating tissue-like structures and organs. The Biolink, composed of cells, biomolecules, and hydrogels, mimics native tissue, offering diverse applications in regenerative medicine, drug testing, and research. With the use of specialized bioprinters, the Biolink is deposited layer by layer, showcasing the innovative potential of this technology. Develop a 3D model. Choose bioinks and validate cell viability. Then, proceed with layer-by-layer deposition using techniques like extrusion and inkjet printing. Lastly, culture the printed structure and evaluate its functional quality for research or medical applications. As we delve into the evolution and progress in bioprinting, the early days of 3D printing marked a significant milestone with Charles Hull pioneering stereolithography, SLA, for layer-by-layer resin solidification. This was followed by the creation of the key object geometry description in 3D printing in 1984, known as the STL file format. Additionally, in 1988, Scott Crump's innovation brought about fused deposition modeling, FDM, enabling consumer-grade 3D printers. These milestones laid the foundation for the current innovations we witness in bioprinting today. As we delve into the evolution and progress in bioprinting, we observe the foundation of bioprinting, originating from additive manufacturing principles for layered object construction. The emergence of living materials marks the transition to using living cells and biomaterials in printing processes. Now let's delve into the latest advancements in bioprinting. Bioink formulations like GelMA and DCM have significantly enhanced tissue integration and function. Furthermore, the field has achieved remarkable milestones with bioprinted skin, cartilage, and mini organs like livers. This has opened up possibilities for tailored organ printing, offering personalized treatment options for patients and reducing the risk of organ rejection. Imagine a world where personalized, functional organs can be created with the help of 3D printing and bioink technology. This innovation holds the promise to address the pressing challenge of organ shortages, offering hope to patients awaiting life-saving transplants. By replicating intricate human organ structures, these advancements have the potential to revolutionize organ transplantation and significantly impact the field of healthcare. Research contributes to societal progress, drives advancements in science and technology, and fosters innovative solutions to complex problems. It helps validate findings, provide evidence-based solutions, and improve decision-making across various fields. By solving problems and fostering innovation, research has a profound impact on society, shaping a better future for all. When it comes to personalized medicine, the focus is on tailoring treatment to individual needs. Advances in genomics and biotechnology have paved the way for enhancing precision in healthcare. Leveraging genetic, environmental, and lifestyle information, personalized medicine is revolutionizing healthcare solutions, providing more precise and effective treatments for patients. Just like a car's engine size sets limits on the complexity of 3D printed organs, hardware constraints play a crucial role in bioprinting scalability. Integrating different technologies for 3D bioprinting is akin to running incompatible software on a computer, a challenge that demands careful navigation. Scaling up production of organs efficiently mirrors the complexities of mass-producing bespoke crafts. Cybersecurity in organ bioprinting is as vital as safeguarding personal information online. Innovations in 3D printing technologies have the potential to reduce costs associated with organ production. Scaling 3D printing for organ production presents logistic and resource allocation challenges. The ethical debate surrounding organ sourcing raises questions about consent, fairness, and accessibility. The implications of 3D printed organs range from addressing organ scarcity to concerns about socioeconomic divides. Layer-by-layer construction of organs using 3D printing is a revolutionary process. This technique utilizes various cell types and scaffold materials to create functional biological structures. The recap of 3D printing process and bioink composition are key aspects to understand the intricacies involved in bioprinting. This lays the foundation for the potential of organ creation, the research benefits, and the possibilities of personalized medicine. The future of bioprinting holds promising goals of advancing medical treatments, research, and technological innovation. Let's delve into the advancements in enhancing blood vessel integration for organ printing. This crucial development improves the vascularization process, ensuring better functionality of bioprinted organs. Additionally, the precision bioink deposition is a significant breakthrough, allowing for more accurate placement of bioink components, leading to enhanced organ structure and function. Today, let's delve into the potential of 3D printing and bioink for organ production. We're facing an organ shortage crisis, but bioprinting offers a solution. By customizing organs for patient-specific needs, we can drastically improve organ transplant accessibility. Additionally, bioengineered organs have the potential to reduce immune rejection risks, leading to more successful transplants. The impact on medical treatments is immense, as this innovation brings hope for a future where organ shortages are a thing of the past.